Day 48, page 1134, Nuclear Physics. Here we have a boron atom with the mass given. This is what's given in the problem, that the mass of a boron atom, that's including the electrons, is that many atomic mass units. But if you take 5 individual protons up here at the top, these 5 protons plus 5 neutrons, and add their masses in atomic mass units, this is what those 10 particles would add up to total mass individually, not as a boron atom. All right, you can see that that's more than what the boron atom is. Now, also, I'm assuming that this boron atom has electrons. So if we take the atom down here, the mass given in the problem, subtract off the mass of 5 electrons, the boron nucleus should have an atomic mass, or actually does have an atomic mass, of this 10.010192 atomic mass units. Whereas the individual particles that make up that nucleus, up here at the top, this is what those 10 particles should have as a mass. You can see that this blue circle, the mass of the individual particles, is more than what the actual nucleus is. So there's a mass defect. There's some quote-unquote missing mass there. And if we simply subtract those two, the mass defect is 0.069513 atomic mass units. That should be atomic mass units. All right, so that is the mass defect for the nucleus. All right, problem 17. So problem 17 then is just plugging into E equals delta MC squared, where delta M is the mass defect. I've converted the mass defect of 0.06953 atomic mass units into kilograms. That's 1.15 times 1.154291 times 10 to the negative 8, 28 kilograms. That's my mass defect. Plugged into delta M right here, times the speed of light squared, and the answer comes out in joules. 1.038862 times 10 to the negative 11th joules. You can convert that to electron volts if you'd like, but that is the binding energy. And if you want the binding energy per nucleon, well, you divide that by 10. So it would be 1.038862 times 10 to the negative 12th joules per nucleon, since there's 10 nucleons.